Welcome back to Chapter 15 on Aromaticity, uh, Lecture 2. This is going to be Part 2. We left off with a discussion of sulfonation of benzene, and here's the slide. You notice fuming sulfuric acid, SO3, in sulfuric acid, or concentrated sulfuric acid is used to sulfonate aromatic rings. As shown here, a substantial amount of electrophilic sulfur trioxide or sulfonium ion is generated. And we can see the generation of the sulfonium ion up here in these two reactions. And down here we see sulfonation of benzene. Of course, benzene's nucleophilic, and the sulfonium ion is electrophilic, and we form a carbocation non-aromatic intermediate, and then we form the product of electrophilic substitution. It is aromatic, which is much more stable than a product of electrophilic addition, which is a non-aromatic addition product. Now let's take a look at the next part of this mechanism for desulfonation. Of course, we just formed sulfonated benzene. So sulfonation is described by the reaction coordinate diagram going from left to right on the next slide we'll see in just a second. So desulfonation is described by the same reaction coordinate diagram going from right to left, as we'll see. And it's illustrated in this mechanism for desulfonation. In sulfonation, the rate determining step is electrophilic attack of benzene by the sulfonium ion. In desulfonation, the rate limiting step is the loss of SO3 with a proton ion from the benzene ring, as you can see on this slide. Here is the reaction coordinate diagram that I mentioned for the sulfonation of benzene from left to right, and the desulfonation of benzene, sulfonic acid, from the right to the left. And of course, sulfonation is going to the right, desulfonation to the left, and this is trying to highlight this portion of the diagram illustrates the transition state for the rate determining step in the forward direction and the rate determining step in the reverse direction. Notice it's the higher of the peaks and it's broader of the peaks. Fidel-Crafts acylation. This is also an electrophilic substitution reaction of benzene. Fidel-Crafts acylation places an acyl group on a benzene ring, and a Fidel-Crafts alkylation places an alkyl group on a benzene ring. So we have acylation here, and we have alkylation illustrated actually on the next slide. Both of these are acylation, as you can see in the products. Either an acyl halide or an acid anhydride can be used for Fidel-Crafts acylation. An acylium ion is the electrophile required by a Fidel-Crafts acylation reaction. The ion is formed by the reaction of acyl chloride or an acid anhydride with aluminum trichloride, a Lewis acid. So you can see what's going on here. Fidel-Crafts acylation must be carried out with more than one equivalent of the aluminum trichloride. Here is the acyl chloride. The acyl portion is highlighted in yellow. Here it is also down in the acid anhydride. And again highlighted in yellow after it's put on the benzene ring, the acyl group. And of course the Lewis acid. Both of these are acylation reactions. Since the product of this reaction contains a carbonyl group that can complex with aluminum trichloride, Fidel-Crafts acylation reactions must be carried out with more than one equivalent of the aluminum trichloride. When the reaction is over, water is added to the reaction mixture to liberate the product from the complex. Notice water is mentioned as second. In addition to acylation reactions, the Fidel-Crafts alkylation reaction can occur in which an alkyl group is substituted for a hydrogen on the benzene ring. The first reaction shows the preparation of the electrophile, R+, that will react with the nucleophile, benzene. In the second reaction, a carbocation is formed from the reaction of the nucleophile, benzene, with the electrophile. Alkyl fluorides, chlorides, bromides, and iodides can be used to generate the electrophile. After alkylation, benzene is more reactive. To prevent further alkylation of the alkyl-substituted benzene, there it is, a large excess of benzene is used in the Fidel-Crafts alkylation reactions. This is to make a molecule of benzene much more available for reaction than a molecule of alkyl-substituted benzene. And of course here we have the preparation again of the electrophile, R+, and here's the nucleophile, benzene, and the R+ is of course the electrophile. A carbocation will rearrange if rearrangement leads to a more stable carbocation. Of course, we've seen this over and over again. When rearrangement can occur in a Fidel-Crafts alkylation reaction, the major product will be the product with the rearranged alkyl group on the benzene ring. Notice that 65% of the product will be the rearranged alkyl substituent. There is increased stability seen in the rearranged product. Of course, that's why it's 65% as opposed to 35%. And the carbocation will rearrange to a more stable species as illustrated down here. When the 1-chlorobutane loses its chlorine, it becomes a primary carbocation. And by a 1,2 hydride shift, this primary carbocation can be rearranged to form a secondary carbocation, which is much more stable. And as a result, it is the one, notice, that is going to be the favorite electrophile binding to the nucleophilic benzene over the primary carbocation that's formed. When benzene reacts with 1-chloro-2,2-dimethylpropane, a primary carbocation rearranges to a tertiary carbocation, as on the next slide. Now in this case, there is a greater increase in carbocation stability, and so a greater amount of rearranged product. In fact, 100% of the product has the rearranged alkyl substituent. Of course, it's going to rearrange to be a tertiary carbocation. Notice the structure right there, which is obviously much more stable than a primary carbocation, which results in 0% of the product. And this is illustrating what we're just talking about and visualizing on the previous slide. The primary carbocation results when the chlorine is removed from the molecule that will be reacting with the benzene. It is now a carbocation and is capable of rearrangement, as you can see illustrated on this slide, through 1,2-methyl shift. A tertiary carbocation is formed. Benzene can also react with carbocations generated from the reaction of an alkene or an alcohol with an acid. Now up here we have an alkene reacting with an acid, and down here we have an alcohol reacting with an acid. And of course there's benzene. And when the alkene reacts with the acid, it forms a secondary carbocation. And it's that is electrophilic and is attracted to the nucleophilic benzene. And then here's alkylation of benzene by an alcohol. Again, the alcohol reacts with the sulfuric acid, and a secondary carbocation results. As you can see here, it is electrophilic and joins up with the nucleophilic benzene. It is not possible to obtain a good yield of an alkyl benzene containing a straight chain group via Fidel-Crafts alkylation. Here is 1-chlorobutane and benzene in the presence of a Lewis acid, and the major product results from the primary carbocation undergoing rearrangement. Notice it's not a straight chain substituent, it's a rearranged alkyl substituent. As opposed to only 35%, this will yield about 65% of the product. This will be 35% of the product. This is the unrearranged alkyl substituent. However, a Fidel-Crafts acylation reduction reaction works quite well. And here you can see benzene in the presence of this particular compound. And you'll notice when it loses the chlorine atom, the remaining portion of this compound does not rearrange. And it readily bonds to the benzene ring, as you can see here. And the two carbon-oxygen bonds in the carbonyl group are replaced with two carbon-hydrogen bonds through reduction. This method avoids using a large excess of benzene in the reaction, as we saw previously. So the acylium ions do not rearrange this when it loses the chlorine. So a straight chain alkyl group can be placed on a benzene ring by means of the Fidel-Crafts acylation reaction, followed by reduction of the carbonyl group to a methylene group. This is called an acylation reduction reaction. The two carbon-hydrogen bonds are replaced by two carbon-hydrogen bonds. Therefore, reduction has occurred. Remember, only a ketone group that is adjacent to a benzene ring can be reduced to a methylene group by catalytic hydrogenation. Preparing alkyl substituted benzenes by acylation reduction also avoids, again, the use of a large amount of benzene, which is a toxic compound. Unlike alkyl substituted benzenes, which are more reactive than benzene, acyl substituted benzenes are less reactive than benzene, so they will not undergo additional Fidel-Crafts acylation reactions. Okay, let's stop there at this point.